Okay, if everyone can hear me, just give me some kind of indication that this actually works somewhere and that the audio is not messed up. Because I don't really know. Um, would assume that you can hear me because no one's responding. Oh, it's just me. Okay. Since no one's watching, I guess I can just start the session and you can like rewatch this video at any stage. Um, so we start off with statistics and probability. So you have the frequency distributions, frequency histograms, and possible plots, and outliers. So frequency distributions are super simple. You just have, oh, what is this? You just have, why is it in this color? You just have a, like that, you have certain data values which you have, and then you just graph them however they are needed. Right, that's basically what the frequency distribution and frequency histograms, same thing. It's just that you have classes of data instead of just data. So the more important thing is box and whisker plots. So when you have a set of data, you have obviously a median. In a box and whisker plot, we call the median Q2. So we'll split up data. So we'll have a bunch of data points. Say the circles are data points. We'd have a median, right, which we would say is Q2. Then we would take the median of these of each data set on the right and the left. So we'd say the right one, this is the median. We would call this Q3, and this one we would call Q1. So that's how we create Q1, Q2, and Q3. Using this, we can structure a few different things. So first, we know that 25% of the data is between each of these quadrants. So 25%, 25%, 25%, and 25%. So each one has 25% of all the corresponding data, as right over there, like so. And what that basically tells us is that this interquartile range between Q1 and Q3, this range over here, that contains 50% of the data. That's Q3 minus Q1 is equal to the interquartile range of your data. And in that range, it contains 50% of all data. And then using this, you create something called a box and whisker plot. So what you would do is you just have a line. Actually, wait, it's not has to have a line. So it's not a line. Okay, so we would have this little whisker thing here. We'd have a line. We'd have a box. So we'd have a line inside the box, and we'd have a line coming out like that. And that's what our plot would look like. What you would do is that you would have a little scale at the bottom here. Over here, where this line is, you'd say that's your Q2. Over here, you'd say this is your Q1. Here, you'd say this is your Q3. And basically and then over here is your smallest value. And then over here, you have your largest value. And that's the whole distribution. You always have outliers. So if you do have an outlier to a range, like something ridiculously high, you graph it outside here as a dot or an appropriate measure. So you would put it as a dot rather than incorporating it into the box and whisker plot, which would make it look really, really weird if you had to extend the line all the way here, even though there's only one data point out there. So that's how an outlier would work, and you would have to figure out if that's an outlier. I'm not sure if IBO has like a specific way requirement for what an outlier is. I'll check that. I don't really. Let me see. Okay, so they do have some methods. WikiHow is where I've sent it to. Okay, okay. Okay, so it seems to be that their way of finding outliers is by simply looking at 1.5 times the interquartile range, so 1.5 times the IQR, and then seeing if it's that far away, if the data is like that far away from the median, or from Q3. What if you'll notice when the data is ridiculously far, 1.5 times IQR away from Q3. I'm gonna double check that. Oh, WikiHow is a horrible resource. Yes, high outliers. That's what we're looking at in IB. We're looking at, so you would do is you check 1.5 IQR times IQR. Then you would look at that rate. You would look at how far that reaches. Everything within that range you would allow to happen after Q3. You'd allow everything inside. Anything outside this would just get cut off like it's an outlier. You wouldn't have it. But everything inside here, that's okay. That's how you would find the outer outliers. I don't think they even look at lower outliers, so this is totally fine. Yep. Then we have central tendency and dispersion. Okay. Median, mode, quartiles, quartile range, IQR, percentile. Okay, so I've looked at quartiles before, right there, which is 25%, 25%, how they're spaced out, but using the interquartile range. And then now we have central tendency and dispersion. So there's different tendencies of certain graphs, which is sometimes important. So it's the first time using this thing, Windows updates. This one does one tendency of a graph. The graph looks like that, right? Like if there's a higher peak over here, and this side is like more data values up here, like if you had like a histogram like that, then it would look like this. That's a right skewed graph. It's right skewed. That's because it's skewed towards the right. In a similar way, it would be if it was like flipped to the left, it would be left skewed. It's basically where this big tail is going. That's the side that defines the skew. And this is right skewed, and the other way around would have been left skewed. Wait, just to check, there seems to be 3 people watching. Is anyone here actually SL? If you're watching and you're SL, just tell me in the chat. If you are SL, if you're SL, please give me some indication that you're SL. Because I'll skip over the SL material and just do HL if there's only HLs watching. So if you're just a HL, then okay. I think everyone is HL. The same as like last time. So I'm gonna go over quite faster over this stuff, so we can get through these things quicker, and look at the harder stuff. So yeah, central test. So we have cumulative frequency. Again, you add up the frequency as you keep going. Cumulative frequency is always going to be increasing, so it will never go down because you keep adding more and more things to it. Keep going higher. Then you have bivariate data, which is this is SL only as well. If you're in the statistics option, HL, you'll also be learning this stuff. It basically outlines creating a scatter plot, and then finding if there's a correlation between 2 pieces of data and whether or not there's a line of best fit actually occurring. It's actually not very difficult. You just you basically rely almost entirely on your calculator to do all of these things for you, and to try and figure out if there's like this actual pattern in the data. So here, now this is the SL and HL material, because is there any indication? No, literally nothing. This is fine. So HL contents. Now we have group data, submit interval values for mean, interval width, upper lower bound. I don't know what this is referring to. I think this is referring to the IQR, probably. Mean interval values for mean interval width upper lower bound. Okay. Let's look at mean variance and standard deviation. So I think the best way to actually think about what the mean variance and standard deviation are is by looking at like a normal distribution. So hopefully, if you're in HL, you've already seen a normal distribution. I mean, everyone should have seen a normal distribution by now. That should be, if you have a normal distribution, your mean is at the center, and we denote mean by mu. Your standard deviation is like, one sec. Just looking at some notation to make sure I don't mess this up. Yeah, okay. And then away from the, it's mu plus standard deviation, mu minus standard deviation. Standard deviation is basically how far away the data is going from the mean, right over here. So you have mu plus, this is the mu plus standard deviation, this is mu minus standard deviation. And then if you want to go here, this will be mu minus 2 standard deviations, and then mu plus 2 standard deviations. Standard deviation is how far away the data is going, how well spread out the data is, basically. If you had a really high standard deviation, then this whole thing would be really stretched out. The way that works is because for a normal distribution, around 34% of the data stays here between mu and mu minus standard deviation, the first standard deviation. 34% stays here, and then you have smaller values as you keep going over here. So if the standard deviation was larger, 34% of the data actually has to spread itself out and become larger to correspond with it. So that's what mean, and that's what standard deviation. Now variance is the standard deviation squared. So variance is equal to standard deviation squared. Variance is just this weird thing we have. It's actually pretty useful in that calculations seem to work much better with variance, like when you're trying to figure out certain things. When you look at the standard deviation squared, the variance works out better. If you're taking the statistics option, you'll see how variance actually comes into play much more than standard deviation. But at least for SL or HL, this stuff is more, it works better in this situation. Okay, so let's look at what's next. Concepts of trial, UPA. Okay, so let's just look over some quick Venn diagram stuff to make sure that we're satisfied with that. If we have a Venn diagram of data A, B, then this data right over here is going to be A intersection B. All three pieces of data, like this one, and this one together, is A union B. Now the way I remember which one is which notation is which, because the notation is important. A union B is a U, A intersection B is just not a U. It's not a U. It's the other way around. That's how I remember it. It's weird, but that's it. That's A union B is the everything, all of these contained. You can also have B one second. You can have B intersection A complement. That means that you need two conditions to satisfy this. You need both. You want B to be true. You also want A to not be true. So you want A. You don't want any A's. That's A complement. It's the opposite of A. So that would mean that would mean all of the stuff here. So that would be right. This stuff would be B intersection A complement. And in the same way, you would have for all of this data, it would be A intersection B complement, as in you want two conditions satisfied, which is that it is in A, and you also want other condition satisfied that it is B complement, means it is not B. So you would look at everything right over here. Now the other one is A complement intersection B complement. So you want A. You don't want it being A. You don't want it being A. You don't want it being B either. So that will look at all your data outside the box entirely. And yeah, another thing is important. This is explicitly different from A complement union B complement. So what this says is that
you want everything that satisfies A complement and everything that satisfies B complement. They don't have to satisfy both of them at the same time. They just happen to they just want to clump all of that data together. So what that would mean is that you don't want anything in A complement, right? So you want everything outside. So that automatically takes in everything outside here. So it takes in this part, it takes in that, it takes in that, it takes everything not in A. And then at the same time, you also want everything not B complement. So everything in here, that also gets taken. All the stuff outside here gets taken. Basically, the only thing that is remaining that doesn't get taken is this center portion right over here, A intersection B. Everything else gets chosen in A complement union B complement. But if you're trying to find out the actual outside area, you would do A complement intersection B complement. So that's important. So intersection means you want both these conditions to be satisfied for all the elements you're putting into it. A complement union B would mean that you're okay with any elements being any to either one of them, basically, and that's what it's saying. Okay, so look at that. P A cap B. Okay, yeah. So here's one thing. This is just a little quick note. That they use this notation, which is that if someone wrote the probability of A, that has line B that says P, the probability of A given B. So what is the probability of A occurring given that B is actually occurring at that point? So we know B is occurring, so it's inside the circle of B, and then what's the probability that it is A? So that's the same. That's equivalent to saying this center portion that's all in black because I put it like that right now. So I can actually use colors. This part. This is A complement B. Let me utilize colors because I'm a good educator. So that's what that is saying, and notice that that's equivalent to this statement right over here, A intersection B. It isn't always equivalent, but here. So now they give a couple of formulas using this. So for conditional probability, so when you have a conditional probability like that, so A given that B exists, it is equivalent to saying this. The probability of A intersection B given that, so probability of A given B is the same as probability of A intersection B over probability of B. So if you ever don't know what's happening, just jump onto here. Almost always, the IB doesn't even care if you understand what's going on. So they want you to identify this part right over here, and then as soon as you can identify that part, and you can plug it in correctly into this formula and understand what's happening, and then understand how to do these parts specifically, then you'll be able to get the marks for it. So they always say use the conditional probability formula that's in the booklet, and then you basically use that. The other two formulas I just skipped over a little while back was probability of A union B is equal to the probability of A plus probability of B minus probability of A intersection B. So actually that should make sense to you. So let me just show you what that looks like. So if we were to have, we just draw the same part again. We have A, B. We have probability of A, this whole thing over here, and the probability of B. So we can say so A union B is just all of this stuff together. So we can have probability A plus probability of B. Now what's being repeated twice? This part is okay, but now this part is also okay, but this part is being added twice. So what we want to do is actually that's a good idea. We can just have like that. This one's also being like that. This part is being added twice. So that's why we take it away from it. So we have, and that's why we do A intersection B, take it away, and that's how we get the formula for that. If they're mutually exclusive events, so that means that they have no intersection at all. So they're just A and B. It's two separate values. That means this formula come into use, and this is you can see this obviously that A union B, both of them to occur together, PA plus PB. And yeah. And then you have independent events again. So this is if the events are in no way connected to each other, then probability of A intersection B is the probability of A times the probability of B. Now this happens quite a lot actually. So this is you might not seen this formula before, but you use this thing all the time. So if you ever have like say what's the probability of me rolling a dice the first time rolling a dice the second time and both times getting a 1. There's a 1/6 chance of it happening the first time and a 1/6 chance of it happening the second time. And those are independent events because the first time you roll a die doesn't affect how you do the second time. So they're independent events, and that's why we can just multiply the probability. So you do 1/6 times 1/6, you get 1/36, and that's how you just multiply them out. So that's how you calculate independent events, and that's just demonstrated in this formula here. And now then we have Bayes' theorem. This theorem exists, right? And if ever you get a question that actually wants you to use Bayes' theorem, you would use this big formula. Insofar, they rarely ever use it. Like you might see this application of it, you'll rarely see this application of Bayes' theorem. It's just this complex theorem that is describing, that is like putting this in different words as to how this works. Actually you can derive this using the conditional probability rules. Bay didn't do much. He just derived it from here. Yeah, it's just a derivation. It's really weird. I've never actually seen many questions using Bayes' theorem. To be sure, I'm gonna go check out if there is a question I can find using Bayes' theorem just to make sure I'm not messing this up. This is strictly HL, obviously. So yeah, so see, there's like all this stuff is like this tucked into this whole topic. Barely any questions. Let me find May 8th. Okay, that's early. 15 TC6. Let's try this one. There's 3 ways to get in school: 30% traveling, 20% to 50% time walk traveling. Okay, so yeah, so they use Bayes' theorem in this one. So there's 3 ways of getting to school. 30% of the time she uses the car, 20% of the time she rides a bicycle, and 50% of the time she walks. And when traveling by car, she's late 5% of the time, and she is late. When riding a bicycle, she's late 10% of the time, like that. And then when walking, she's late 24% of the time. That's how you distribute it here. Then they take the conjugate of that, put that there, put that there, put that there. Look at the complements. And then given that she was on time, find the probability that she rides her bicycle. So again, they look over here. So they read the tree diagram. Then you have your probability. You use your Bayes' theorem, which is the probability that she rides her bicycle, given that she is on time. So that's the L complement. So given that she's on time, and then literally this is the whole big formula of Bayes' theorem, the whole big thing, and that's literally they just plug in all these values one by one, and they get this calculation, and that's that. That is how you would use Bayes' theorem to solve this. So you would look at all these different things occurring, then you would try and figure out how you could interpret Bayes' theorem, which, by the way, is equivalent to just saying the probability of B intersection L complement over the probability of L complement, right? Which is just that's the previous formula, not Bayes' theorem. It's this one. So even the time when they want you to use Bayes' theorem, there's always some other formula I can use, or some other method of doing this that might be faster for you, or you like it more, or whatever. It's a weird formula. Rarely ever used. So let's get next one. So discrete and continuous. Okay, yeah. So let's look at this. So let's look at probability distribution. So let me look at what these are. Okay, so first let's think about what I'm gonna just combine discrete and continuous. I'm not discrete is SL, by the way, but since I think they're mostly HLs here anyways, it'll be better if we just do a combination of both to better understand this stuff. So if we had a probability distribution, this is a continuous probability distribution, by the way. Right over here, it's continuous probability distribution. Or if it was discrete, there would be like little bars like this.
of the probability. Different probabilities, so there'd be different x1, x2, x3, x4, if that was discrete. What the expected value basically says is what is the expected value of what I'm doing, right? So basically what it does is that it's like if any of you have done chemistry, actually no, I'm not going to use that example. It's basically finding like the weighted average of what you're going to get. So probably I'm going to get x1 is just like this low probability, but probably I'm going to get x2 is something higher, x3 is even higher, x4 is even higher, and all of these different things are different probabilities. I multiply them by that probability, and then I take the average. So basically I'm taking the average of every single value over here. So let me just like show you why that works and how that works. So say we had a 2, right? And we have a 0.1 possibility of a 2. So we have a 3, and we have a 0.3 possibility of a 3, and we have this. We have the 4, which is the remaining, which is 0.6, right? And so that's 4. Basically, what this says, we want to find the average value or the expected value of this little probability distribution. So the way we would think about that is 0.6% of the time we have a 4, 0.3% of the time we have a 3, 0.1 time we have a 2. So that basically means like 60% we have 4, 30% we have 3, 10% we have 2. Wow, that's a bad 10. So yeah, but 10% we have 2. Basically what this means, if we took like 100 trials, right? 60 of them would be a 4, 30 of them would be a 3, and 10 of them would be a 2. And then it's easy to find the average. So what you do is you do 60 times 4 plus 30 times 3 plus 10 times 2, and then you would divide all of that by 100. So you would have 240 plus 90 plus 20, so that's 240, 260, 350, so 350 divided by 100, and then you find the expected value is 3.5. That's what the expected value is. So basically you're taking your average. But we don't usually go through all of these steps and get to here. We just do it immediately. What we do is we do the probability of 4, 0.6 times 4, plus the probability of 3, 0.3 times 3, plus the probability of 2, which is 0.1 times 2, which will give you the same answer. So what you're doing is you're just multiplying probabilities to like find a weighted average of all the values. And that's what the expected value is. So that's why you have 3.5 as your expected value. That makes sense because 3.5 should be somewhere around here, so there's more 4s and less 3s and 2s. So that's what an expected value is. Now so we denote this by as this, a sum xf of x of your whole probability distribution, x of x. That's what you would denote your the expected value of a discrete function to be. Now for the same thing, you'd have the expected value of a continuous function, but now since it's continuous, you can't obviously use these stuff. So you need to take the integral of xf of x dx. Now, one thing I found really weird about IB is that they categorize topic. They categorize topic 5 before topic 6, where in reality you need literally everything in topic 6 and topic 5. So I don't understand why they did that, but yeah, here. So this is the formula from negative infinity to infinity. So your points would be negative infinity to infinity. But notice that actually, let me just erase some of this stuff. Erase some. So you might be a little intimidated. How are you going to evaluate negative infinity and infinity as a proper integral? Usually when you have continuous functions, note that they give you bounds. So if they give you a function, say they'll give you a function x squared, they're not just going to give you a full x squared function. They'll give you a bound. They'll say it stops here at this point, and it stops here at this point. And between these 2 points, the total area is equal to 1 underneath this thing. And everywhere else, the probability continuous distribution is just 0. So when you say negative infinity infinity, you might have, say, a bound over here as 0 and a bound over here as 1. You might only need to do it from 0 to 1 to actually get the expected value, because you're only integrating where the actual function is defined as per the question. So it's not just negative infinity, infinity blankly. It's you think about where it's defined and how you're going to be doing it that way. So yeah. Let me check. Okay, so now we have another interesting little property, which is calculating variance. This is why we use variance so much. It's because it's a lot easier to calculate than our friend the standard deviation, and it makes a lot more sense as well. Why this is happening. So let me just pull up. Sorry, not the right one. Okay, so actually let me not clear the canvas. So the variance of x is equal to the expected value of x squared minus the expected value of x squared. Now the distinction between these two is that what you do over here is that you take x squared of any given for each f of x, you actually look at you correspond it to the x squared. So say the previous example where we had a 2 and a 3 and a 4 and their individual probabilities, instead of looking at it as just as 2, 3, 4, what you would do is you would actually look at it as 4, the probability of 4, the probability of 9, and the probability of 16. You get that. Then you would use those respective probabilities. If you remember 0.1, 0.3, and 0.6, you would use those probabilities with it, and that's how you would run that. You'd run that through. You would get this, and then after that, you would look at your original expected value, square that, take it away from this. You get variance. This is a faster way to calculate variance than plugging in every single data point into your calculator and then telling the calculator to do the variance, or even worse, manually calculating the variance using every data point. This is much faster, and you should always aim to look how you can do this. In the formula booklet, they discuss some methods on how you actually calculate these things. So if you have a discrete random variable, what you would do is you would look at the sum of x squared times the probability of x occurring. So remember that you basically multiply the x squared part. So you don't look. So say you wanted to find out the probability of 2, we just plug in 2, find the probability of 2, and then multiply that times 2 squared. And then after you finish all the sums of that, of all the different variables, you take away the mu squared. The reason that they take away mu squared, which is the mean, is that the expected value is actually equal to the mean for these for a discrete and a continuous random variable, because we, again, as I said before, it's a weighted average. So we would expect it to actually be the mean, and that's what the mean is, and that's how you take away the mean squared, and that's the formula over here for discrete random variable. And then same thing you look at for a continuous random variable. It's x squared f of x of dx, which is an integral minus mu squared. One interesting property, I don't know if this is in the calculus, I think it should be, this little portion over here, this is also important, this is just important overall. If you have a, so let me just take a quick, if you have a continuous distribution, this could actually, if you have any function at all, and you wanted to find the mean of that, the average value of that function, you would use this formula. This is the formula that you would use to find the average value of the function. So like, where's the average value if you looked at every single y value of a function? You would actually use this function. This is how you use it in actual calculus as well. Not just, this is a result derived from calculus. So that's just a fun note. So let's look back here. Okay, so mode, median. Okay, so when we're looking at continuous distribution functions, there's a few different properties that we need to be mindful of. So let me do it again. So if we had a continuous distribution like that, to find the mode of this continuous distribution, the mode basically means what is the most likely value, what is the one that we're definitely going to have. So you would do is that you would actually find the peak, the maximum, which has a derivative of 0, right over it. So you would differentiate whatever your function is. You would take du dx of f of x, and then you would set that equal to 0. So when that's 0, you would find that maximum point. And note, sometimes in the bounds that they give you, this doesn't happen. It'll be like this. Also, one more thing. This could be a minimum. So you want to make sure you don't get a minimum. You want to make sure you actually have a maximum. So sometimes if in the equation, you can have, say, these are two bounds that they've given you, x and x1, and this is your function. Note that this never occurs, right? This will never happen because it's always a slope of, like, always a negative slope. So you know that this is your peak value. So you need to check if that is the case, if that is actually the highest point. Another thing that could happen is they could give you two bounds, x1 and x2, and it could look like this. In which case, yes, there is a d of dx equals 0, but that's a minimum. You don't want to find the minimum. You want to find these maximums and check which one is higher, and then say that that is actually what it is. This happens a lot, and it gets confusing. So you need to make sure you don't always jump to this for mode. Let me just erase all of this. And then we have the median. So the median is basically where 50% of the data lies. So remember when we were looking before, we were looking at how the 25%, 25%, 25%, 25%, the median is the 50%, 50% splitter, right? So what you do is when you have a continuous distribution, and you want to find the point at which the area here is 0.5 and the area here is 0.5. So if you had some starting restriction x, then you would look for what value of not y, so what value of like m, let's call it m, what value of m do you need to get to until it becomes 0.5? So the way you would do that is you would look the integral from x to m of f of x dx is equal to 0.5, and you would solve for this. So you know what f of x is, you know what your starting bound x is, so you're solving for m. So you would manually integrate this. You would plug in the bounds into it, set that equal to 0.5, and solve for m as where's the median. So where the area is equal to 0.5. And yep, that's how you would do that. So then probability density functions, I think for some reason I've covered it. Yeah, I basically covered it. We have a ping. Let me check. Oh, it's okay. It's fine. Yeah, so now let's look at the different kinds of distribution. So there's binomial, there's Poisson, and there is normal distribution. So normal distribution I already discussed earlier as to what it is and what it does. But there's some more information that's important, especially in relation to the standardized normal. I'll come back to binomial and Poisson, but I'll just go to standardized normal. So a lot of the times in questions, what they'll do, you need to know how to manipulate this information very carefully, which is like, this is your standard normal, right, with a mean of 0, right? It has a mean of 0. Wow, I really can't draw. It's like next level bad, like. Now it looks like a theta. This is horrible. This is fine. This is honestly okay. Yeah. So we have a mean of 0, and then they'll say you have a standard deviation of 1. So the first standard deviation is over there, and it's over there, and you have 34%. This is specifically what you'll be doing in paper 2. Actually, I don't doubt there'll ever be a paper 1 question specifically to this. So you have 34% there, 34% there. That's a -1, by the way. So if you had a standard normal, right?
Basically, you have something called a z-score. So what the z-score says is how far away certain data is from the mean. So how many standard deviations away something is. So if something is 2 z-scores away, that means that it's 2 standard deviations away from the mean. So in this situation, if you had a z-score of 2, it would be whatever value of 2 is far over here. Right, so that's what the z-score says about a function. Now, the z-score is important because you don't necessarily need to know the actual values of the mean and the standard deviation to calculate the z-score. Well, all you need to know is the area. So sometimes in a function, they'll give you some some standard normal distribution, right, with some unknown mu and some unknown standard deviation. So you don't know what they are, but they'll tell you. That at some value of x, a percentage lies inside that. So the some percentage of all values lie below this x value right over here. All a values, right? So what you would actually do, what the z-score can tell you, is you can find out the z-score of x of this data point x naught by looking at the standard normal, right? So you look at when does the standard normal have that percentage coming in from the left. So you try and find out when you have 8% over here, what number occurs over here, like what number x occurs over here, then that is the z-score of this or this value x naught. So you can plug that into your calculator. So depending on what calculator you have the norm, the inverse normal. And what you would do is that this you can plug in. So it'll always ask you. It'll ask you what's your mean, what's your standard deviation, and for that, at least in my calculator, the T-Inspire CX, it automatically sets those as 0 and 1. It automatically sets that as to the standard normal because it knows that I'm trying to find z-score. I'll plug in the percentage. So say it's 12%. I put 0.12. And 0.12 would be my data point. This will give me the z-score of x naught. Now I know the z-score of x naught. I get another piece of useful information, which is this right over here. Z is equal to x minus mu over standard deviation. So z is equal to x minus mu of standard deviation. Now I know what the x value is, and I know what the z-score of that x value is because I know the area. And then you'll have a mu and a standard deviation, which are unknowns. Usually they'll give you another data point somewhere along this line. And then you'll be able to set up a new equation with a different z-score, but with the same mu and standard deviation. Then you can do a simultaneous equation solve. One important note I'd like to make is that if your data point is on the right side of the normal distribution, say it's here, right, and they say this is 30%, right? This is 30% of the data. This 30% of the data is on the right of this data point x1, right? When you're plugging into the inv norm, you should not put you should not be putting if you put 30%, it's going to give you a different z-score to what it actually is, because when it calculates the z-score, right, what it does, it looks at this whole area to the left of this function. So it looks at this whole entire area. So what you're telling it when you're saying that it's 30% is that this is 30%, when that's not the case. This is actually 70%. Okay, this is actually 70%. So then it'll give you the correct z-score, because this z-score on this side, right, this is a negative value. This is a negative value because it's negative standard deviations. It's on this direction of it. And if you put 30% in, it'll give you 30% on this side. It'll give you a negative z-score. You might mess it up. So you need to make sure you look at 70% if it's on the right of the mean. So you need to make sure you look at that correctly when you're doing it. So that's basically how, I think that's more of important, is like how your calculator actually does these calculations. So it doesn't know which direction you're doing it from, or it doesn't know whether it's from the mean or what. It just does it from the left. So we're on the very left of the function all the way to your data point. It's going to tell you that z-score, so wherever it is, and that's what it's going to do. So yeah, that's that. Then we have the binomial distribution. So the binomial distribution it's just like a and again, it goes back to the binomial theorem. Okay, so it goes back to the binomial theorem, which is the probability. So binomial distributions will always be used when you have some sort of choice being made in a theorem. So like if the probability of a success or failure. This is super common, and then especially when success has some probability p, and then failure has that probability 1 minus p. That's important. This little thing that's happening here. 1 minus p usually denoted by q. So the way that you would calculate that is that you would look at because combinatorics and the binomial expansion theorem are directly linked. You could use this formula. So n choose x, p to the x times 1 minus p to the n minus x. So that's how you would evaluate the binomial distribution. Now, rarely ever do you actually need to evaluate the binomial distribution, because it's almost always just plug it into your calculator. Like as soon as you detect or know that this is happening, you plug it into your calculator, and then you solve. So the hardest part about a binomial distribution question is figuring out if it is a binomial distribution question or not. And then you know that you should know that when they ask a success or failure question. So when they're saying what is the likelihood of this occurring, and then you know the likelihood of not occurring, that's success as it does occur, or failure, it doesn't occur. And so you should think about that. There's a really good problem. It's called a lift. It's about a lift. I think it's one of the papers. I'll find the question and send it to you guys if you really want it. But the question basically says like it gives you quite a few different things you need to do, and then it says what is the probability that that these many people can go onto an elevator. And in the previous parts of the question, you found that probability, and then you need to use the binomial distribution. So, anyway, the one more thing, binomial distribution works in trials, right? So you do the same thing several times. What is the probability of it happening p time? What is the probability of it happening x number of times? I completely forgot that. I don't know why I forgot that. I think it's because I'm just used to binomial theorem now. So it's also about trials. So if you did something n number of times with the probability, it will happen x times. So if I say an elevator, the probability of an elevator breaking down is 0.5. If I ran the elevator experiment 8 times, if I ran an elevator 8 times, what is the probability of it breaking down 3 times? And then I would use that formula. So I would say n would be 8, x would be 3 times. The probability of 0.5 to the power of x, which is 3. Then 1 minus p is 0.5 times 8 minus 3, which is 5. So, and then I would calculate that, and that would give me my probability. And then you go see you have a mean and variance for a binomial distribution, NP and NP times 1 minus p. If you're in the statistics option, this will become useful. You will actually, you'll learn the derivation for why this formula works. So yeah. So next we have the Poisson distribution. So that's so the Poisson distribution is used when you have you have a recurrent thing occurring within a given time period. So instead of having a success or failure, you have like a given time period. So this happens on average 3 times in a week. 3 times a week it happens. And then what is the probability of it happening 2 times? And that's where the Poisson distribution comes in. So what you would do is you would literally you'd have a Poisson distribution with a certain mean. So you plug this into your calculator, and it'll ask you what's the mean of your Poisson distribution. You plug in the mean. Then it say, okay, what x value do you want? 2. So you plug in your mean is 3. Then you say, what x value do you want? 2. You plug in the x value of 2. It will give you your it'll give you your Poisson distribution right after you do that. So and that's how you basically calculate that. It's quite simple. So sometimes the Poisson distribution, they'll ask you a cumulative Poisson distribution, or so the cumulative functions for binomial and normal are pretty okay. Like what you would do is you would just put like for these like say you wanted to find every value less than 3. You would just put 0 and 3 for a binomial normal, or every value greater than 3. You would put 3 and then some ridiculously high number like 1,000 for binomial and normal. That works. For Poisson, that doesn't work. So you need to make sure you have definite numbers. So you can't just put some ridiculously high numbers. Say they wanted to find a cumulative probability distribution from 3 over 3. And what's the probability of happening over 3? So you would not just put 3 and then 1,000. That rarely ever actually works. What you should do is you should do 0 and 3 and then 1 minus whatever that cumulative gives you. The cumulative is always in your calculator, so you should learn how to just quickly transform the question, how to put it into a cumulative. Everything should be in your calculator. Make sure you learn your calculator really well for statistics. Your mean is the mean is just the same. The variance is also the same as the mean for a Poisson distribution only. The expected value is the mean, and the variance is also the mean. This is the only distribution where this occurs. Don't just do this everywhere. And yes, that's the end of topic 5. Make sure you know how to use your calculator. Look at your calculator guide. They're online. Everything is online. Make sure you know how to use your calculators. Statistics is almost all using your calculator. They're just giving you these things. They're literally giving you the answers here for all this stuff. You should know how to use your calculator so that you can give them back an answer really quickly, really fast. They don't even give you they don't even waste time with explaining how you got this half the time. So you just plug in binomial NP, find your value state, you know what it is, just give the answer at the end. And now we move on to calculus. I just like to take like a 5 minute break right now. So I'll be back in like 5 minutes. Just go to the washroom.
Okay, I'm back. I'll just continue with calculus. So first of all, we're gonna look at the limit definition. Just look over that quickly. I've never actually seen a question that specifically requires you to know it, but it's best if you understand the derivation of the derivative. So if you have a function and you have some x value and some f of x value, you're trying to find the closest value, x plus h, and f of x plus h. And you're trying to like minimize that minimize that slope as much as possible by minimizing h. And finding the instantaneous at x. So what you would do is you would have f of x plus h, which is your y value, minus other y value, f of x. Then you have this value, x plus h, minus x, which happens to be h. That's your limit definition of a derivative. So you can use the same notation here. Yep, right over there, like that. That's what your actual formal definition of a derivative is, and that's calculating the instantaneous slope at any point, which is your derivative. So obviously that's just not that. You would have to have your limit notation, which is as limit of h approaches 0. It's not always easy how to calculate this correctly to get your final derivative, but yeah. That's your first principles. So one other important thing is continuity and differentiability of a function. Those are two important things to have a function. So that's important because it comes up as a question sometimes, and people don't know what to do. And that was what my classmates had in one of the mock exams, which they didn't learn this because, it took them as a surprise. It's very common in AP though. So if any of you have done an American course, it's very common. So if you have any function, right, there's two conditions for this to be a function. One, it needs to be continuous at all points, right? So it needs to not have any holes. It can't have any jumps. It can't have any cuts. So it can't go like that and then continue over there as a function. It can't do that. It has to be differentiable. So it needs to be differentiable at all points. And what that means is that you can't have these cuts and corners. So you can't have this. Because it's not differentiable at this point. You might think, oh, you can just put a line there. But what about infinitely small to the right? Then it's like a line like that. So it's like a jump in the differentiation. You can understand actually how why it needs to be differentiable as well, because you can, if you looked at the derivative of this function, you would see it looks like this. If you have a derivative of the absolute value function, it's 1 over here, and then negative 1 over there. So it's a 1 at 0, it suddenly becomes a negative 1. That's a jump. You can't have that jump in the differentiation. So you need to, that's what you need. These are two conditions that you need to meet. I don't know why I raised that. I'm very stupid. You have your continuity and differentiability. And usually what they'll do is they'll give you like a piecewise defined function. So the f of x is defined by g of x between from x is less than a, and then when a is less than, and x is greater than or equal to a, it's like b of x, say. That's what your piecewise defined function would say. And now and so they'll give you like some there'll be some variable you need to solve for. So g of x will look like everything will be defined, even the a will be defined, except there'll be like some variant inside g of x or b of x, like something that says it's not exactly what it is. Like it'll be like sine of x plus k, for example. That could be a thing. X plus k. So they'll say, what is k? They'll try and find what is k inside this. If this is a function, and the second thing you check for is the derivative equal to each other. And if usually what happens is that if you have both of these, you can have like a jump like that. That's not allowed. You can't do that. And yeah, that's what says it's a function. This is important.
And this is especially important if you're in the calculus option. So this stuff you look into much more detail as you go to the calculus option. Yeah. Is this? I wonder what this is. Let me just check what this is. Oh my god, that's amazing. I'm just I'm gonna use that. Okay. Uh, um. So increasing, decreasing functions, second derivative, concavity, maximum. Okay, so this stuff is as far as I know, I've only seen it in like SL questions because they expect you to think that it's actually quite easy. They expect you to know this stuff like as if it's just basic knowledge, and it's in some stages just completely ignore it after that. So first, let's look at increasing and decreasing functions. So how you would check if it's always increasing or always decreasing. So yeah, so you know it's always increasing, always decreasing based on what the derivative is doing or based on some properties of the original function. So why? So you look at this and you say it's always, so let's look at the cubic function, it's always increasing. It's like that, right? So the way, this is a cubic function, f of x equal to x cubed, right? The derivative of this is equal to 2x squared, right? Now x squared is always going to be positive. 2 is also positive, so 2 times x is a positive number, it's always going to be positive. That's why it's always increasing. And we know it's always increasing. Another way to check if everything something is always increasing, we looked at this before in the functions topic, which is you would check if f of a is equal to f of b, then a is equal to b. So that just says that it never goes back down. It never makes like a turn. It never goes like that and then turns back downwards. So it never, for any two y values, a is always there's never going to be for one x two different y values. So if the function of a, if the y value for a and the y value for b are the same, that must mean that a is equal to b. So if you can show for this, you also show it's always increasing. And the same way for always decreasing. So this is how you would check if it's always increasing or always decreasing. And another word for what we would say for this is monotonous function. Also expanding on monotonous function, what we would call this in the functions unit was injective. So it's injective. It's always, there's no point where every x value corresponds to one y value and one y value only. That's what this means. Monotonous function. Always increasing, always decreasing. Note there is a small difference between always increasing and non-decreasing, right? Because if something is always increasing, that means the derivative is always positive. But if something is non-decreasing, then that means that it never goes down. But it's possible for it to be at a zero slope and then go back up. That's what this x cubed function is. It has a point over there where it's non-decreasing. So it's like just a zero slope. This is not a super important distinction, but it'd be better if you don't get confused between what these two things are at any stage. So yeah. Then we have second derivative and the concavity. So what this basically says is if you have some weird looking function like that, right? The first derivative would say that that's a line over there. Now the first derivative would say that at this point it will be a positive value, and then over here it would continue being a positive value. One second, I'm messing this up. So at this point you'd have a positive value, but it's slowly curving more to zero. So what you would do is you would the positive value slowly curving more to zero, and then it starts flipping and it becomes a negative slope right around over here. It becomes a negative slope, then hits zero again. Yeah. So it hits zero again and goes up. But basically, I don't know. I'm really bad at drawing. That's why I can't do this correctly. I think it would be better if I gave this in Desmos to explain how the change is happening. I'm not very good at drawing. We have x cubed. Actually, let's make it a weird x cubed. Nah, this is x squared. And then we 2x squared, and the derivative of the 4x. So the two different things that's happening here. So first, let's look at what the connection is between x cubed. Let me scale this by some factors so it becomes a little nicer. So like a half, right? So it becomes a little spaced out. And all these would have to be changed by basically, what this is that this is the cubic function right over here. What the first derivative is saying is what is the slope at any given point. So this at over here is always positive. It's always positive, and it goes slower and slower until it hits a critical point, which is just a slope of 0 right over there. So it hits 0, and it starts going up again. It continues staying all positive. It's always positive. This whole thing is always positive. That's why this is a monotonous increasing function. And it keeps going straight up. It goes straight up, and it keeps going higher and higher, and the slope just keeps increasing. Now, if we look at the derivative, the second derivative of this function tells us something slightly different. So what the second derivative is telling us something known as concavity. So this is a negative concavity over here, has a positive concavity over there, and a zero concavity. And whenever the second derivative hits 0, that's an inflection point right over there. So to understand what concavity is, it's just simply it's simply when a point looks like this. That's negative concavity. And then when something looks like this, that's positive concavity. So if you see over here, it's negative concavity over here. So it's looking a bit like that, like that. Then over here, it looks up like that, like a smiley kind of face. So that's how it's looking up, positive concavity. Then over here, you have an inflection point when concavity changes, and that's at 0. So that's basically what this whole business is about. And that's what concavity is. Concavity is helpful when you're trying to find maximum and minimum points. So when you're trying to figure out if a derivative's, if you found a derivative point where it's equal to 0, so if I just open the whiteboard again. If you found a point of the derivative where it is equal to 0, where it's, oh my god, I'm horrible. Point is equal to 0, and there's a point where it's equal to 0. You can figure out, so you know this is 0 point, you know this is 0 point, but you don't know whether or not these 2 points are maximums or minimums. So you can check if this is a maximum if the concavity is negative over here. Then you know that this is a maximum because the shape of the function is like that. So then you know the point at 0 is a maximum right over there. If the concavity of this one is a positive concavity, then you know that this is a minimum because it's like that, and that's going to be a minimum at the bottom. And that's how you check for concavity, like to check for the maximum minimum slope. Usually you don't even need to do this though. There's other ways to check and know. I never actually used concavity in an IB test to check for derivatives and to check for maximum points, minimum points. It's usually obvious in other ways. But that's important to know. And I think that's much more important in SL as well. Any important pings? Why do I even have a ping? Oh, okay, some random server. Okay. Yeah, so that's a graphical behavior. It goes to graphical behavioral function, and how these things define each other. So what they're saying about each other's functions. Note again, this is the derivative of this, right? So this describes behavior about this function, specifically about the slope. So the second derivative describes the first derivative's information about slope, and in the same way that the first derivative will inform the original function's behavior of slope. And the second derivative function also stores certain information about the original function, albeit not very much of it. So yeah, and you can obviously go between these using integration. But then you have to look at a constant, and you don't ask to know for sure. Okay, so higher derivatives. We just discussed higher derivatives. I think, yeah. How to do actual calculus, product rule, quotient rule. I find that you should never mess up with differentiation. Purely because they're giving you literally everything. Especially for HL, it just give you this big list of like things that you need to use. And if you can break down anything into this little thing over here, you can break down the chain rule, product rule, and the quotient rule. This is the easiest thing in the world. It should be the easiest marks. You should never lose any marks in any differentiation at all. However, you can make it super complicated to try and check if you don't get phased out or anything. But let me just go over the rules real quickly and how we can use them. So we have chain rule, which is that if I have a function g of f of x, right? Oh, it actually made that a circle. Undo. Yeah. So d of f of x, and then we were to make that. We wanted to find the derivative of this. We wanted to. What am I doing? I have an eraser. So I wanted to take the differentiate this d of x of this whole thing. The way I would do that is I would take the derivative g of x. I pretend f of x is like just a part of g of x. I take the derivative of that, and then I would multiply it by the derivative of f of x. So multiply by the derivative of the inside. So you look at the inside, you multiply it out by the outside, and this is how you have the chain rule. Then you have the product rule, which is d of dx of g of x times f of x. And the way we do that is, oh my god, that's ridiculous. Why does it keep doing that? I'm just gonna remove this. I thought it would be useful. It's obviously not. U of x f of x, and this would be g prime of x times f of x plus f prime of x g of x. This is the easiest. This is actually the easiest one to remember, and the fastest to use is just this. I often found that I like then there's obviously the quotient rule. So there's a different formula for how you would do that. So then that's written right over here. How you would do that. So using this notation. I don't like using that notation. I don't like. I mean, I like using Leibniz notation. That notation there, but I don't like the quotient rule much because I never really found a very intuitive way to understand it. So I always use the product. Almost always use the product rule, except I like take the denominator to the power of -1 and then do all my calculations like that. But you can use either one, and especially in tests, you have a formula booklet, so you don't need to remember these two things. You can just use a formula booklet. Obviously, it'd be beneficial if you did remember these things so that you don't actually waste much time doing the test, like trying to find the formulas. But it's your wish. It's your wish how you utilize these things. Just make sure that you don't waste too much time on all of this. So. And obviously you have all of these things. A lot of these you should try and get infused in your head as you keep practicing. Yeah, all the practice that you're doing. And this will get infused. But again, if you ever forget it, they have it all written out here. Because for IB, they're not testing how much you can remember. They're testing how you can use the information given to you. So they have all of this given to you. How are you going to find what you need to know from that? This is a note from Anne. So let's move. Yeah, we're moving on. We go to related rates, and implicit. So Andrew wrote he doesn't like related rates. I like related rates. I like playing around with them, especially. Actually, I think the best way for me. So the related rates is where they'll give you a whole bunch of. This is why it becomes very useful to use Leibniz notation. To use the one that uses like d of dx or like d of dh or something like that, right? The Leibniz notation, that's super useful for related rates because it easily cancels stuff out. So basically, they'll give you some obscure rates. They'll give you some rates, right, which you have to try and convert into Leibniz notation. So you have to try and say. So maybe they'll say y is related to y the rate of change. Why do I cross stuff out like that? So they'll say that y is related to h. So y changes with respect to h. So that we do dy dh is equal to like, so they'll give you something, and then they'll say then they'll give you some other, and then they'll give you some other information like hidden. They'll give you like some connection between y and h. So they'll be like y is equal to 2h squared, or sometimes they'll give you like some like volume sort of relation. So y is equal to 2h squared, and then they'll say, okay, now solve for like some other variable or something like that. And then they'll tell you to figure it out. I think the best way for you to understand how related rates works is if you look at a problem. So I'm going to find a problem right now for related rates. So let's look at what am I doing right here? Okay, yeah, this is what we do. So guess what I'm going to find. Yeah. Actually, this looks slightly harder than I thought I wanted it to be. Let's not do this one. Do what I've done before. Find one. But this is even harder. Let's stick to this. So water trough is just 10 meters long, uniform cross section in the shape of a semicircle with radius 0.5 centimeters. So they're looking at this little part over here. It's partly filled with water, as shown right over there, with the part of the cross section. The center of the circle is O, and the angle KOL is theta radians. So the volume of water is increasing at a constant rate of 0.008. So it's 10 meters long and the shape of a semicircle with radius 0.5. So find an expression for the volume of water in the trough in terms of theta. So they'll find the area of the segment, which is 1 over 2 times 0.5 squared times theta minus sine theta. Wait, what are they doing here? Why would they do that? The area of this whole segment, theta minus sine theta. Why are they doing sine theta? I don't know. Let me think as to why they would do that. Half times 0.5 squared. Okay, fair enough. I don't know why they're doing that. That's. Oh, okay. I get it. I get what they're doing. They did some simplifications here. I don't know why they would do that, but basically what they did is they find the area of the segment right over here. So what they did is they found sine theta, which is this part over here, so they could find the triangle area, and then they basically take that away. It's a minus sine theta from the actual theta over here, which is the whole segment's area. So they found the area of the segment, they found the volume is the area of the segment times 10, and then they found like a volume, so they found a formula for volume. So when I told you earlier how they're going to give you some information that you're going to try and like manipulate, that's what I meant. So you have to try and manipulate it to get this information. Over here, they like guide you towards that. So then it's calculate d theta of dt when theta is equal to pi over 3. So then what you would do is you can immediately calculate, you would just differentiate all of this stuff in respect to t, because they find d theta dt. So you need to find a way to, so currently is v is equal to 5 over 4 theta minus sine theta. Now you have to do in d of dt. So you do d dt everything, you keep going, you keep plugging in everything. You keep you do all the differentiation you need to do. You also implicitly differentiate, you get d theta over dt. I'll explain implicit differentiation just in a second. And then you get this little you get a little formula for it. You solve for d theta dt, and you get your method. Now another way to do it, which is written over here, is d theta dt is equal to d theta over dv times dv over dt. This is using Leibniz notation. So you're splitting up the problem into an easier problem. So then you can calculate. So then you can calculate, and then basically what they do is they can plug in the formula that they found earlier of d theta dt. So you have dv d theta. So they would flip this around, put it around, and do all these weird things, and they would have to calculate this formula, do everything, work it through, and yeah, basically that's basically it. And yeah, that's how you would solve related rate problems. Yeah, so yeah, that's it. So the next part is implicit. Yeah, so implicit is basically it's actually I feel like implicit is just the chain rule, but like hidden really carefully. So what you would do is that if you have y is equal to say xy, right? And then you wanted to find, now obviously I know this will cancel out, I know, but let's say we wanted to find the derivative with respect to x. So I do dy dx, right? D of multiply that, and then is equal to d of dx of
xy, right? So that's equal to d of dx of xy, so that would be x times dy dx, right? So that you would find out, you do d of, so we'd have d of dx times x. So d of dx times x is just, so first let's do the product rule. So we just keep x as it is, and then we take the differentiable of y. So well, for y, normally y would just become 1, right? It would just disappear as a variable, and then it does do that. It just disappears as 1. Then you also need to do the chain rule with it. So because y actually stores information about x, we need to pretend like it has some values inside of it that need to be chain ruled, and that's why we take the derivative of the inside, which is dy dx, and then we add that to the different d of dx of x is just 1 times y, right? And then you have this formula, which is dy dx is equal to x dy dx plus y, and then you would solve for this basically. And over here is actually quite simple to solve for this. You just move it to the other side, and you could solve for dy dx, and that's how you would get the actual value. So the dy dx is just the use of the chain rule, and you should think about it exactly like that. So now we have a few different more, so indefinite integrals, all functions in 5 and in 6. I don't know what he's referring to over here. Okay. Okay, there's quite a lot of things here. We're taking group with substitution to smooth parts. Composite with linear function. Yeah, okay, so indefinite integrals. There's a bunch of standard integrals. So now I hope that this, because it was a revision session, you should probably have a pretty good understanding of integration. So you should be able to know why most of these are working. Some of these slightly more difficult than others, but again, they're the derivations, so that the reasons why these occur are not required in IB. So these are required in AP though, and they might be in the calculus option. I'm not sure. I don't think so though, the calculus option. But over here, you don't need to know. You just need to know that they exist. There's some important. So let me look at some important methods before I look at all this stuff. Some important methods for integration and substitute, and so we have, I think over here we have substitution by parts. So I think SL does not learn that, and HL learns certain extra things. So SL does not learn how to do this stuff, but I'll just go over integration by parts, integration by substitution. So if you have, I think best to give integration and substitution by. Sounds like we have one. No, not this. We have the integral of say 3x plus 2 squared dx. You can do the integral of that. Now that's so because it's 3x plus 2, it's kind of like a obviously you can try and do this on your own without having to use integration by substitution, but just because it's a very simple example, I'd rather do it by substitution. So what you can do over here is that in order to make the problem a little easier, more analytical, rather than doing it in your head, you said u is equal to 3x plus 2. Then you could also take you would differentiate with respect to x on both sides. So you do du dx is equal to 3, and then that would just basically tell you that that dx is equal to 1/3 du. And then you can plug into the equation over here. So what you would do is use the integral of u squared, and times, we found that dx is equal to 1/3 du. So then you could say 1/3 du. And then you can rewrite that as 1/3 times the integral of u squared du is the same as whatever you're going to get over here. And then you would solve for whatever this is, and then you could basically plug in whatever values you find are important. And you would calculate that by just saying 1/3 times 1/2. 1/3 times 1/3 u cubed. Yes, that is how you do calculus. Plus c. So plus c plus a constant. Then you plug in 3x plus 2 back into u, and that's basically your formula. And then you're done. But one important thing that I just like to mention is how you would use the bound. So sometimes you can have a bound from a to b for a certain function.
the way you would do that is by you would plug in for x for that bound. So what you do is you said, so if I wanted to find out what is the new bound for the u function for a, so this is I would put ax and this is bx. So what I do is I would plug in ax. So I said u is equal to 3 times ax plus 2. Then whatever u is, that will give me some new AU, and that's my new lower bound for u. And the same thing for BU. So you just plug it into whatever your substitution is, and then you should be able to change the function entirely if you're doing a definite integral. And that's substitution, integration by substitution, by u substitution. Who knows actually watching it? Yeah, you guys, someone's still watching. Wait, is the quality down? Why is the quality down? Is that a problem? Is it just my internet? Oh, there is a HD option. Okay, cool. So you can then you have integration by parts. That's another method. Integration by parts is basically when you have any like sum of two different integrals, and then they also give you the formula for integration by parts in your formula booklet. So how you would use it. So if I had integral of uv uv dx, what I could do is that I could just calculate. I can find uv. This integral is the same as uv minus the integral of v u dx. So look at how that would work in terms of like actual good notation. Yeah, this is a much better notation. So if it's integral of u dv is equal to uv minus f. So basically, you look at I'll just go through an example. I think a good example to explain how integration by parts works is one of the hardest ones I've ever seen. I mean, not the hardest one, it's just the one that no one understands how to do. Is this one, the integral of arc sine of x dx. This is a non-standard integration by parts, and most people don't know how to do it. So the first thing they'll do, they'll look at your. Wait, is Discord Canary opening? No, don't open right now. Like that. If we had a formula booklet, I have a ping. I have 2 pings from random channels. Okay. The formula booklet shows. The formula booklet doesn't say anything about the integral of arc sine. They say a derivative of arc sine. So you know the derivative of arc sine, and that's what you'll use to your advantage. You would convert this into 1 times the arc sine of x dx. That's what you're going to be doing. And what you do is you'd set u is equal to arc sine of x, right? And then you would say du is equal to the derivative of whatever this is, which is some weird complicated function. So if I just check my formula booklet, it's 1 over square root of 1 minus x squared. Minus x squared. And then v would be dv, so the dx over there. Dv could be 1, which should be 1 dx, and then this should just be x. So that's how you do it, and you notice that u dv, so this is the integral u dv is just that, is arc sine times 1 dx, and then so you have to change that, so you have to do uv. So now you look at uv, you do arc sine of x, x arc sine of x minus the integral of v du. So the way you would do that is you would do x over 1 square root of 1 minus x squared dx, and that's how you have to solve for that. Now notice this is much easier to solve because you can do a u substitution. So you can set u equal to 1 minus x squared, then du is equal to negative 2x dx, which then you can rearrange for x dx, then you can calculate this integral much more easily than this previous one. And then whatever the final answer is, you'll get a value for your for arc sine of integral of arc sine of x dx. So this is your technique for using integration by parts. And let's keep going. So def integrals is a condition. And then we have one more final thing, which is the area volumes around a around like an axis. They have formulas for this right over here. So basically, what this says is that your confound is the area under a curve. So this should be very basic stuff for integration by now. That is the volume of revolution. So that's basically when you're trying to find out how it would look like when you revolved something around an axis. Now this works well because this actually works because of the area formula. So what you basically do, you create a function, and then you basically at every y value of that function, or every x value of the function, the depends which one you're doing, you would look at that what circle that creates around whatever axis you're looking at. And then if you're checking that, and then you sum all of those circles up together. So that's what they're doing. So they have pi y squared. So if you're looking at it in terms, if you're doing it in terms of x, right? So that would be around the x-axis. So yeah, this is a good example. It's already open as well. If you're looking at it in terms of x and the x-axis, so you're revolving it around the x-axis like that. You look at this y value, y value, y value. Look at all the little circles they create over here. The circles they create. Let me just actually sketch this out. You're looking at the circles they create around here, the circles around, and the circles around here. All of those circles, you'll sum all of them up, and that's why you get the formula for around the x-axis. Note, you can also do it in terms of the y-axis, because sometimes it's easier to do it in terms of the y-axis, and you would need to rewrite it in terms of the y-axis in order to do the volume of revolution for that one. There's kinematics problems. Unfortunately, I have to leave soon because my parents are telling me to go somewhere. Kinematics, I can link video where you can understand how the kinematic equations derived. But if you're in HL, I don't think they even ever look at kinematics equations. That seems to be an SL concept. But as an exercise, if you feel like you really want to do it, then go ahead and try and derive the Suvat equations from physics. So go search up the Suvat equations online, and try and think about why they exist as they do, and try and think about how they came. So that'll be the end of the revision session. I know I didn't go over calculus very well, but it's because I was in kind of a hurry. Okay, thanks. Bye.